Miles of locomotives sit parked dead on desert storage lines stretching for miles, some barely a decade old. Meanwhile, units built before the moon landing's afterglow had even faded are still hauling mainline freight every single day. Airlines retire jets after 20 years. Trucking fleets turn over in under 10. So why does North American rail, one of the most capital-intensive industries on the continent, keep running 50-year-old locomotives while newer ones collect dust? The answer isn't nostalgia, and it isn't neglect. It's a calculation that starts with a question most people never think to ask. What exactly makes a locomotive old? A single new mainline locomotive carries a price tag of up to $4 million. When a Class 1 railroad like Union Pacific or BNSF looks at its roster, it is managing a massive fleet of 7,000 to 8,000 active units. Replacing even a fraction of these fleets with brand new machines goes far beyond routine maintenance. It represents a multi-billion-dollar capital allocation choice that lands directly on the desk of the chief financial officer. At this scale, procurement decisions alter corporate balance sheets for decades. Committing billions to purchase new locomotives binds a railroad to a specific technology, locking up precious capital that could otherwise fund track upgrades, advanced signaling, or terminal expansions. The weight of these decisions is staggering. A mistake in fleet planning can depress a railroad's return on invested capital for a generation. Meanwhile, freight volumes fluctuate constantly. Committing to massive capital expenditures during a downturn risks leaving highly expensive, depreciating assets sitting idle on storage tracks, a visible drain on profitability. This turns the physical locomotive from a mere tool of transport into a complex financial instrument. The choice between purchasing new power or maintaining legacy equipment is fundamentally a strategic gamble on operational flexibility. A brand new locomotive represents an immediate, inflexible cash drain that must be depreciated over 30 years. In contrast, an older, fully depreciated unit represents financial freedom. It costs almost nothing to park when cargo volumes drop, and it can be reactivated quickly when demand surges. For fleet planners, the challenge extends far beyond finding machines capable of pulling freight. They must manage billions of dollars in capital risk while preserving the ability to adapt to an unpredictable economy. The decision to buy new is further complicated by a structural reality. Railroads do not shop in a highly competitive open market. Only 2 manufacturers produce mainline freight locomotives for the entire North American continent: Wabtec, which acquired GE Transportation in 2019, and Progress Rail, a subsidiary of Caterpillar. This tight duopoly controls the supply of heavy motive power, leaving buyers with few options and little bargaining power. It is a market where buyers are captive to the constraints of the sellers. Wabtec dominates the sector, commanding approximately 71% of all new build deliveries. Progress Rail produces the remainder, delivering only about 120 units in 2024. This extreme concentration of manufacturing power has created a massive supply bottleneck. By the end of 2025, Wabtec's order backlog swelled to $27 billion, proving that the factories are running at absolute capacity. For a railroad looking to expand or modernize its fleet, this means facing long queues and limited build slots. Ordering a batch of brand new locomotives often requires waiting 18 to 24 months for delivery. The pressure of this duopoly has even boiled over into legal warfare. In 2023, Progress Rail filed a federal antitrust lawsuit accusing Wabtec of anti-competitive behavior, alleging that the company used its dominant position to restrict competitors' access to key parts. Though the parties reached a confidential settlement in early 2026, the litigation exposed the deep friction within a highly consolidated supply chain. With only 2 builders, tight production capacities, and lengthy wait times, railroads find their purchasing choices severely restricted. A new locomotive is not an off-the-shelf purchase. It is a scarce asset with an extended delivery horizon. This physical supply constraint makes the prospect of rebuilding older, existing locomotives on a 6 to 12-month timeline look increasingly practical. Instead of waiting years for a duopoly to deliver new machines, railroads can bypass the factory floor entirely, taking control of their own schedules by turning to their own maintenance shops or independent contract rebuilders. This preference for legacy equipment is not a symptom of simple corporate stinginess or a stubborn refusal to modernize. In the high-stakes environment of freight rail, sentimentality and penny pinching are quickly weeded out by intense quarterly scrutiny. Instead, the persistence of 50-year-old locomotives represents a calculated, highly rational business decision. When evaluated by the specific metrics that actually govern railroad operations, these older platforms do not just compete with modern alternatives, they frequently beat them. To understand why, one must look past the shiny paint and digital displays of a factory-new unit and focus on how a railroad measures utility. The industry does not value novelty. It values availability, the guarantee that a locomotive will start and run when called upon. It values tractive performance, the raw physical ability to grip the steel rails and pull thousands of tons of cargo up a grade. It values lead time, getting a machine on the tracks in months rather than years. And above all, it values life cycle cost, minimizing the total capital expended over decades of grueling service. On every one of these fronts, legacy diesel-electric platforms offer distinct advantages over their multi-million-dollar descendants. By shifting the focus from the calendar age of a machine to its actual performance on these core operational metrics, the decision to run older power ceases to look like an outdated compromise. It reveals itself as a highly practical asset strategy that turns the traditional economics of industrial machinery entirely on its head. To understand how a machine built in 1975 can match a modern equivalent, we must first change how we define a locomotive. In industries like trucking or consumer electronics, a vehicle is treated as a single, integrated product. When the engine dies or the technology becomes obsolete, the entire machine is typically discarded. A diesel-electric locomotive operates on a completely different engineering philosophy. It functions as an assembly of independent, modular systems built around a single, virtually indestructible foundation: the steel underframe. This underframe, along with the outer car body, represents the permanent physical core of the asset. Fabricated from massive, high-strength, fatigue-resistant steel, these frames are over-engineered to a degree rarely seen in modern manufacturing. During daily operations, a locomotive frame experiences massive forces. It must support the weight of a 16-cylinder diesel engine, a massive electrical generator, and thousands of gallons of fuel, all while enduring the physical shocks of pulling trains weighing 20,000 tons. Yet because the frame does not experience the intense thermal cycles, high-speed friction, or chemical corrosion of the internal engine parts, it is structurally insulated from the primary causes of mechanical wear. When a railroad sends a decades-old locomotive in for a comprehensive rebuild, technicians do not simply repair worn parts. They strip the machine down entirely to this bare steel chassis. The engine, the generator, the electrical wiring, the traction motors, the air compressor, and the operator's cab are completely removed, leaving nothing but a naked slab of structural steel on wheels. Work crews inspect this frame using non-destructive testing methods, such as magnetic particle and ultrasonic testing, to locate tiny micro cracks in the welds or steel plates. If they find any fatigue damage, they cut away the compromised section and weld in new, high-grade steel, often adding reinforcing plates and gussets to strengthen known high-stress areas. Once the structural integrity of the frame is verified, the reconstruction process begins. Technicians install a newly manufactured or completely overhauled diesel engine. They drop in rebuilt traction motors, which convert electricity into physical movement at the wheels. They run miles of brand new electrical cabling throughout the chassis, replacing old, brittle wiring that has decayed over decades of service. The old mechanical control systems, once reliant on hundreds of physical switches and relays, are replaced by modern computerized modules that monitor performance and diagnose faults in real time. Finally, the cab itself is often completely replaced or refurbished, receiving modern heating, ventilation, air conditioning, and ergonomic controls. The finished locomotive rolls out of the shop, looking and performing like a brand new machine. It carries a fresh coat of paint and modern electronics, yet on paper, it retains its original build date from decades earlier. This reveals the core paradox of railroad fleet management. A locomotive labeled as 50 years old often contains very little original material. The engine, the traction motors, the copper wiring, and the computerized controls might be only weeks out of the factory. The only truly ancient component is the steel underframe beneath them. This distinction between the frame and the components it carries is the key to understanding locomotive economics. By treating the structural frame as the permanent, long-lived asset and the internal machinery as replaceable wear-out parts, railroads escape the rapid depreciation cycles that plague other transportation industries. A trucking company cannot cost-effectively replace every single component of a semi-truck while keeping only the chassis rails. The labor and parts would exceed the cost of a new vehicle. The massive physical scale of a locomotive makes this modular replacement strategy highly efficient. The steel frame represents a permanent platform that can support 3, 4, or even 5 generations of engines and electronics. Once this fundamental engineering reality is clear, the rest of railroad economics makes perfect sense. Under the Environmental Protection Agency's regulatory framework, a quiet legal mechanism completely reshapes the financial calculation of fleet modernization before a single mechanic picks up a wrench. This system is codified in Title 40 of the Code of Federal Regulations, Part 1033. Under these rules, a locomotive's emissions tier is permanently tied to its date of original manufacture, not the date it is rebuilt. This regulatory design creates a massive advantage. If a Class 1 railroad rebuilds a locomotive originally manufactured in 1975, that machine remains certified under Tier 0 guidelines. Even if technicians strip it to the bare steel frame, replace the entire prime mover, and install modern computerized controls, the law still treats it as a Tier 0 asset. This means the rebuilt unit is legally allowed to operate under the significantly more lenient emission standards of its birth year, avoiding the need for complex modern exhaust scrubbing equipment. Compare this to the alternative. If a railroad decides to bypass the rebuild shop and buy a brand new locomotive, it is dragged immediately into the toughest regulatory bracket, Tier 4. Since 2015, all newly manufactured locomotives must meet strict Tier 4 limits, which mandate a 90% reduction in particulate matter and an 80% reduction in nitrogen oxides. To achieve this, new builds must carry advanced after-treatment systems like selective catalytic reduction and diesel particulate filters. These systems add immense mechanical complexity, increase the risk of road failures, and introduce substantial ongoing maintenance costs. This regulatory divide was not an oversight or an accidental loophole. During the rulemaking process, documented under EPA Docket HQ OAR 2003-0192, the Association of American Railroads aggressively lobbied to protect the industry's long-term capital investments. The final rule, published in the Federal Register on April 3, 2007, codified this original manufacture provision in Subpart C. It was a deliberate structural compromise. The government recognized that forcing legacy frames to retroactively adopt Tier 4 technologies would be cost-prohibitive, potentially paralyzing the freight network. For fleet planners, this makes an old steel frame more than just a structural asset. It is a legal shield against modern regulatory costs. By choosing to rebuild a 30 or 40-year-old core instead of buying new, a railroad legally circumvents the millions of dollars in compliance hardware and ongoing maintenance that a new Tier 4 machine demands. Long before a locomotive rolls into the shop to be rebuilt, the legal framework has already tipped the scale, making the preservation of old iron the most financially rational path forward. On the desk of a railroad chief financial officer, the physical reality of heavy machinery is translated into a stark financial calculation. A brand new mainline locomotive carries a price tag of $3 to $4 million. In contrast, a comprehensive ground-up rebuild of a legacy unit costs between $1 million and $1.5 million. This represents a direct capital saving of 40 to 60% per unit. When multiplied across a fleet modernization program of 100 locomotives, choosing to rebuild saves a railroad up to $250 million in upfront capital. This is precious liquidity that remains on the balance sheet, free to fund track upgrades, positive train control systems, or yard expansions. But the financial logic goes far beyond the initial purchase price. The second vital variable in the modernization equation is lead time. Ordering a new locomotive forces a railroad to wait at the back of a highly consolidated manufacturing queue. With Wabtec's order backlog climbing to $27 billion, the wait time for a brand new locomotive routinely stretches from 18 to 24 months. In a volatile shipping environment where freight volumes fluctuate rapidly, a railroad cannot afford to wait 2 years to respond to rising demand. Rebuilding existing assets completely bypasses this market bottleneck. A typical modernization program takes between 6 and 12 months from the time a donor locomotive enters the facility to the moment it returns to active service. The actual shop flow for a complete overhaul is often just 12 weeks. By running these programs through their own maintenance shops or independent contract facilities, railroads escape the manufacturing queues of the dominant builders. They regain absolute control over their own capacity schedules, putting modernized locomotives back on the rails, pulling freight in half the time of a factory order. Viewed from the inside of a railroad headquarters, this asset strategy contains no room for sentimentality. It is a highly rational, unavoidable business choice. A rebuilt locomotive delivers nearly identical tractive performance, improved reliability, and updated electronics compared to a brand new unit, but does so at a fraction of the capital expense. By treating the indestructible steel underframe as a permanent foundation and renewing the modular components around it, fleet managers effectively decouple their operations from the constraints of the new build market. The older locomotive ceases to be a relic of a bygone era. It is a highly strategic financial asset. In commercial aviation, weight is the ultimate enemy. Airlines allocate up to 40% of their operating budgets purely to fuel, meaning every extra pound carried drains profit. Because newer passenger jets offer massive aerodynamic and engine improvements, older, heavier airframes rapidly become financial liabilities. They are retired after 25 to 30 years because the savings from a lighter, modern model easily outpace the cost of buying a new plane. Railroads operate under a completely different physical law. On a steel track, weight is not a liability, it is an asset. A heavier locomotive pushes its wheels harder against the steel rails, creating the necessary friction to pull thousands of tons of cargo without slipping. Fuel also makes up only 15 to 20% of a railroad's operating costs, cutting the financial penalty for running older, thirstier engines. While a lighter airplane is a better airplane, a heavier locomotive is a stronger pulling machine. This physical divide splits the life cycle math of the two industries, allowing 50-year-old steel frames on the ground to outlast the most advanced structures in the sky. The physical advantage of a heavy steel frame is magnified when railroads change how a locomotive sends power to the rails. For decades, diesel-electric locomotives relied on direct current, or DC, traction motors to turn their wheels. While dependable, DC motors are limited by mechanical brushes and commutators that wear down under heavy loads. When a DC locomotive tries to pull a heavy train up a steep grade at low speeds, the motors can overheat, causing the wheels to slip on the steel rails. To solve this, railroads do not need to buy brand new locomotives. Instead, they strip the old DC systems out of a 40-year-old frame and install alternating current, or AC, traction equipment. This is not a minor mechanical tweak. It is a major leap in physical capability. AC traction motors contain no brushes to wear out, reducing motor maintenance costs by up to 40%. More importantly, AC systems use computerized inverters to constantly adjust the frequency of the electricity sent to the wheels. This precise electrical control increases adhesion, the physical grip between wheel and rail, by up to 100%. A locomotive that once struggled to maintain grip below 10 miles per hour can now crawl up a mountain at 3 miles per hour, pulling thousands of tons without slipping. By converting old DC frames to AC power, railroads gain the pulling performance of a brand new machine at a fraction of the cost. In the late 2010s, a sweeping operational shift known as Precision Scheduled Railroading, or PSR, redefined how North American carriers moved freight. This strategy, adopted by major Class I railroads including CSX, Norfolk Southern, and Union Pacific, replaced the traditional model of holding trains until yards were full with a strict, fixed schedule system. To reduce costs, railroads began running significantly longer, heavier trains, which required far fewer total locomotive units to move the same volume of cargo. The immediate consequence of this transition was a massive, industry-wide contraction in active fleet requirements. Norfolk Southern, for example, reduced its active locomotive fleet by 22% in the wake of its PSR adoption, sidelining hundreds of units and recording a $385 million asset rationalization charge. Across the continent, railroads consolidated their operations, sending thousands of completely functional, serviceable locomotives directly into long-term storage sidings. This sudden surplus of motive power completely altered the financial math of fleet replenishment. Under normal operating conditions, a railroad might buy new locomotives to replace aging units or to handle traffic growth. But with thousands of parked, fully paid-for locomotives sitting in reserve, the economic justification for purchasing brand-new multi-million-dollar machines vanished. This vast reservoir of spare power acted as a physical buffer, shielding railroads from the need to order new equipment even as older units reached the end of their traditional service lives. Instead of disappearing, the old locomotives became the ultimate insurance policy. If traffic spiked, railroads did not need to wait 2 years for a manufacturer to build new units. They simply pulled a stored engine out of reserve, serviced it, and put it back to work. PSR did not just make operations leaner, it fundamentally broke the replacement cycle, turning excess legacy hardware into a permanent barrier against new capital investments. Inside the cavernous maintenance shops of Omaha, North Little Rock, and Huntington, a different kind of balance sheet governs locomotive life cycles. This is the ledger of human expertise and institutional memory. When a mechanic opens the hood of a classic EMD SD42, there are no surprises. For 50 years, the specialized tooling, the diagnostic routines, and the physical parts inventories have been precisely tailored to these specific machines. Union Pacific's Locomotive Maintenance Academy and similar Class I training centers have spent decades certifying thousands of technicians on EMD 645 and 710 engines, as well as GEFDL platforms. Every wire route, torque specification, and oil spectrograph reading is second nature to the workforce. Introducing an entirely new locomotive platform disrupts this established workflow. It demands millions of dollars in diagnostic software, proprietary wrenches, and completely new spare parts pipelines. Most importantly, it introduces a steep learning curve. Complex computer-controlled emission systems and delicate Tier 4 electronic setups bring unknown failure modes that can paralyze a maintenance yard while technicians scramble to diagnose the problems. By choosing to rebuild a familiar platform, a railroad bypasses these hidden transition costs entirely. The parts are already in the warehouse, the specialized tooling is already on the racks, and the mechanics can perform a complete engine overhaul blindfolded. When a machine works reliably, and the people tasked with fixing it know exactly how to keep it running, sticking with the same old platform becomes the smartest long-term decision. California's Air Resources Board introduced an in-use locomotive regulation that directly targets the industry's reliance on aging frames. Beginning in 2030, the rule proposes to ban any locomotive older than 23 years from operating within the state, while requiring all newly built line haul power to be zero emission. This state-level offensive directly challenges the EPA's federal framework under Title 40. If California's rules survive legal challenges from the Association of American Railroads, they will create a fragmented national network where 50-year-old frames are legally locked out of major West Coast ports. Beyond state borders, the federal government is drafting a potential Tier 5 emission standard. A new tier could close the remanufacturing loophole entirely by forcing rebuilt locomotives to meet modern, ultra-low emission targets, stripping older frames of their regulatory immunity. At the same time, the technology beneath the hood is fundamentally shifting. Pilot programs are testing alternative propulsion systems that cannot simply be retrofitted into a mid-century chassis. Wabtec is currently trialing its FLX drive battery electric platform, while Progress Rail is testing its Joule hydrogen fuel cell demonstrator. These zero-emission designs require completely different weight distributions, cooling systems, and structural layouts than traditional diesel-electric setups. A heavy block of lithium-ion batteries or a high-pressure hydrogen tank requires a chassis specifically designed for their unique crashworthiness and thermal management needs, making legacy steel frames physically obsolete for the next generation of power. Even if regulations remain unchanged and technology stalls, the strategy faces an absolute physical limit. The pool of rebuildable donor locomotives is finite. Every year, more classic GP40s, SD42s, and early Dash 8s are permanently retired, damaged in derailments, or cut up for scrap. Railroads are consuming a non-renewable resource. Once the inventory of structurally sound, pre-1973 and Tier 0 frames is exhausted, the raw material for the rebuild pipeline will simply cease to exist. The delicate balance of capital savings, regulatory loopholes, and legacy engineering is not a permanent solution, but a temporary alignment of economics and law. The 50-year-old locomotive continues to haul freight today, but the clock is ticking on the very conditions that keep it alive. The question isn't how much longer these steel titans can survive, but whether we can ever build anything truly worth replacing them. In an era obsessed with disposable technology, the 50-year-old locomotive stands as a masterclass in industrial logic. It proves that true progress isn't about starting over. It's about building things meant to last. What do you think of this strategy? Let me know in the comments.